So hello everyone, today we'll be solving today's LeetCode problem of the day. Let's see what is it. Okay, so it's a hard problem, like the tag is hard. You have n computers, you are given the integer n and the zero indexed array batteries where the ith battery can run a computer for batteries of 5 minutes. You are interested in running all the computers at a time, like simultaneously, and you can reset at most one battery. Sorry, you can insert at most one battery into each computer. After that, at any integer time moment, you can remove a battery from a computer any number of times. Fine. What we need to compute? Maximum number of minutes you can run all the n computers simultaneously. All right. Okay. Uh, is there any greedy way of doing this? Is there any greedy way of doing this? Can we do this? A greedy solution, maybe. The total time I have is this thing. The total time I have is this thing. 3 plus 3 plus 3, 9. And I have two computers, so 9 by 2 is 4. Sorry, 9 by 2 is 8. And here the answer is 4. Okay, wait. Okay, wait. I know this. I know this. How far could it go? How far could it go? I know how far can this time can go. So I have a upper bound and lower bound. If we see here carefully, we have an upper bound and lower bound. Let's take a file, go.tldr. All right. So I know that the maximum time, can either be anywhere ranging from at least 1 minute. 1 minute it has to last somehow, because all the like you can see the constraints, right? Batteries of I is always greater than or equal to 1. So it should at least last 1 minute anyway. And the upper bound is sum by n. What sum by n? It's nothing but it's sigma bi I equal to 0 to n minus 1 by, okay, this thing is actually some m, right? Let's say there are m batteries, and okay, so this is the expression. It's always in this limit, right? It's always in this limit. The worst it can do is it can just stay for 1 minute. If it's like, let's say you have two computers and you have two batteries which can last 1 minute and 1 minute. So what you would do, you would plug the one battery to one computer, one battery to another computer, and it would last for 1 minute. That's the worst case. That's the worst case. And how far could it go maximum? It can go till sum by n. So let's compute that sum by n first. Or okay, wait. Let's engineer more upon this problem. You have this one and this range. So is this a monotonic range? This is a monotonic range, right? Sum by n. This is a monotonic range. All right. Or else, in layman's terms, it's a sorted array. It's a sorted array, which means you can apply a binary search here. Instead of sequentially checking, is this the max time, is this the max time, is this the max time, instead you could apply binary search. Okay. One more thing important to know, why when can we apply binary search and when can we not? If it's something like 1 to infinity, you don't know this upper bound, or it's some minus infinity or some undefined value to 1. Sorry, not 1, some k. In these cases you cannot apply binary search because the bound is not defined. The bound is not defined. But since you know here, you know both start and end here, you can actually apply a binary search here. You can. All right. But it won't be a simple binary search. We would be checking for uh, condition, some particular condition. Okay. So usually these types of problems are known as binary search and answer. Let me browse it for you. It's buffering. If you see the GFG article, it's a simple thing. Okay. There's nothing to complicate about it. So it's the simple binary search. And okay, this is for square root computation. So you in case of square root also, the value always is between 1 to n, square root of any number, or let's say 0 to n. If it's 0, square root of 0 is always 0. And the worst it could go is n, which is also not possible, but yeah. you can always say it's in a particular bound. Okay, so yeah, uh, we are not going to read the whole article now. Binary search on answer basically works like you have the main binary search function. You have the main binary search function, and usually in binary search, what do you check? If answer equal to mid or something like that, answer equal to mid. So isn't this a greedy check? Isn't this a greedy check? Very what can I say? Simple greedy, I would say. Doesn't involve much of a brain. Answer equal to mid. This is basically a greedy kind of check. Like you know what you're checking for. So it's basically greedy. So you have a greedy check here. You have a greedy check function here. Instead of checking answer equal to mid, instead you check if greedy check greedy check of mid. Whatever the greedy check function may be, it should be a Boolean function. So whatever it is doesn't matter. If greedy check of mid is true, that particular mid is the answer. And since we have to maximize it, okay, let's take this. Let's do this in VS Code so that I can write some good code and also explain you. What's the name of the vector? Batteries, right? Batteries of size. Okay, they didn't mention a size, but we'll take some size. And we need to print this thing, max runtime, which would take max runtime. Is this right? Yeah. And batteries, batteries vector. So now we'll be writing this max runtime function. Fine. So one thing we know is we'll be having a greedy check here. So what's the upper bound? Sorry, what's the lower bound of this? Let's take start equal to, what was it? The lower bound of this thing was, at least it would run for 1 minute simultaneously. So lower bound was 1. Lower bound was 1. And what's the upper bound? Sum by n. Sum is currently not there here. Let's compute sum very easily. Alright, sum is also computed. So we have a sum now. We know the lower bound and upper bound. Now all we need to apply binary search to maximize something. Binary search to maximize something. So this is a very basic code. It's binary search to maximize. In this, what happens? Normal binary search condition while start is less than n. Let's compute mid. I hope you know this expression. It's written in this way to avoid overflow. Okay. If you write start plus end, if start is a big number, end is a big number, start plus end will be an even big number, which would obviously maybe it may cause an overflow. Okay. So we have this a mid. If your mid undergoes a greedy check, let's forget for now what's the greedy check. If your mid undergoes a greedy check and returns true. So let me declare a function to avoid this error squiggles which are irritating. For now, let's forget what's this greedy check. Okay, just forget what's this greedy check. And let's take, yeah, now there are no error squiggles. And if greedy check of mid is true, let's take a variable named answer, which is initially equal to -1. Since -1 cannot be an answer, so yeah. And answer equal to mid. And if you find a mid, let's say if you find a mid, let me tell you, we are maximizing upon the binary search. So if 1, 2, 3, 4, 5, this is a sorted array, right? Let's say your mid somehow landed on 4. Your mid somehow landed on 4, and uh, it had to undergo greedy check. It returned a true value. It returned a true value. So this returns a true value. That means mid is a valid answer. Mid is a valid answer. Mid is a valid answer. And you want to find, since you want to maximize it, you want to maximize this answer. What would you do? Let's say there are a few more stuff. Okay, you would check in the right half, so that you basically check, is there an even bigger answer? Is there an even bigger answer? Is there an even greater answer? So what you move to right by doing start equal to mid plus 1. All right. Otherwise, one thing is very clear. If this is some random array, if this is some random array, if you cannot run computer simultaneously for 3 minutes, can you ever run computer simultaneously for 4 minutes? Is that even possible? No. You can't even run it for 3 minutes. How can you run it for 4 minutes? So it's not possible. So instead you'll be checking for the left half. You'll basically move to the smaller value. Basically move to the smaller value. So by moving to the left half, end equal to mid minus 1. At last, whatever the answer you have, it would be a maximized answer which you would return here. Would be a maximized answer which you would return here. Now coming to the greedy check function. How can we actually check uh, whether a time is valid or not? So I hope binary search to maximize this concept is clear. It's a very basic concept, by the way. If you even think for a while, it's easy to figure out. Now coming to the greedy check. Okay, since we are applying greedy on the batteries, and it's completely dependent on the computers also. What all are dependent? Let's take them as input. Let's take long n, and also let's take vector int ampersand batteries. Okay, this should be int n instead. Whatever. Okay, we gave it an extra comma, which is giving a trouble. Now let's add the same things here. It's dependent on batteries, it's dependent on mid, it's dependent on n as well. Fine. Now, thinking of the greedy check, this is the most crucial part. The rest of the problem is just a piece of cake if you are able to figure this greedy check out. So, how can we actually derive that? How can we actually derive that a particular value time, a particular value of mid is a valid time? Like your computer can run for this amount of time. Your computer can run for this amount of time. Computers can run for this amount of time. How can you do that? That's the crucial part here. Is it doable? I guess it's doable. So if I have a time, let's say, okay, so let's say I have a time t. Let's say I have a time t. So if I just take, uh, if I just take number of unsatisfied computers as u, if I take number of unsatisfied computers as u, initially all the computers are unsatisfied. Let's keep it as when can you say a computer is satisfied? When can you say a computer is satisfied? If it's having some unit of battery, let's say it's satisfied. Initially, all the n computers are unsatisfied. Let's say I have a time t. Initially, all n computers are unsatisfied, and uh, I would iterate through the batteries. I would iterate through the batteries using a for loop. I need not write the for loop. I would iterate through the batteries. If if a particular battery, let's say there's only two cases. There's only two cases. One is this case which we talked earlier. Like there are two computers. There are two computers. Initially, two are unsatisfied, and you give them one energy or one battery, 1 minute of what was it? You give it a battery so that it can run 1 minute and 1 minute, both of them. So the total would be 1 minute. The total would be 1 minute. This is one case. What if you have two comma? This is the batteries. Then it would run 2 minutes. Then the computers would run 2 minutes. And if we observe, for let's say you have a time t, can this run for 1 minute? If t equal to 1, what would happen? If t equal to 1, can this run for 1 minute? Can this run for 1 minute? Let's see. You have two computers. You have batteries 2 comma 2. So 2 minus 1 is possible. 2 minus 1 is possible, and 2 minus 1 is also possible. So it can actually run for 1 minute. So let's say you have a time t and u equal to n, the number of unsatisfied computers. What would you do? You iterate over the iterate over the batteries. You iterate over the batteries and say, um, if a particular battery's value, if a particular battery's value is at least t, is at least t, if b is at least t, if b is at least t, a particular battery's value b is at least t, then what can you do? You can actually satisfy one computer out of this. You can actually satisfy one computer out of this. So you do unsatisfied equal to n minus 1. You do unsatisfied equal to n minus 1. Like previously it was n, you do unsatisfied equal to n minus 1. At least t, at least t. Let's say, if it's not at least t, if it's somehow less than t, if it's somehow less than t. So what you do, you need to check if that less than t value, let's say t dash, if there are multiple other t dashes, if there are multiple other t dashes, you sum up all of them, t1 dash, t2 dash, all of them, how many ever you find the battery values, which are, let's call them b1 dash, b2 dash. You sum up all of these, and store this sum and say, with this sum, how much time can I run? How much time can I run the unsatisfied batteries? So um, all you need to do is this whole sum, the whole sum, whatever is there, b1 dash, b2 dash, let's call it some, the whole sum as s. Okay, the whole sum as s, and s by t, s is the total time, right? S is the total time. S is the total time by the given time, like it should run within this time. If this is greater than or equal to, if the total time, if it can run. So basically what are you saying? um with this particular sum, using b1, b2, b3, you can run, let's say, some k pcs. You can run k pcs. If that particular k is greater than or equal to n, that means you can run n pcs also. You can run k pcs. At most you can run kpcs. At most you can run kpcs. If that particular k is greater than n, it's good. Like you can run 5 pcs, but you only need to run 4 pcs. Like k is 5, n is 4, then obviously you can run 4 pcs. If k is 5 and n is 5, that's also fine. You can run 5 pcs at most. You can and you have 5 pcs only, even that's fine. So now the greedy, since we derived the greedy, all we need to do is write the same thing in the greedy check. Let's say long unsatisfied unsatisfied computers is equal to n. Let's say unsatisfied computers is equal to n, and let's say that particular value s is initially 0, which we derived via greedy just now. Okay, and mid is the time. Mid is the time. We would iterate over the batteries for auto 1% battery in batteries. If a particular battery is at most, if it's at most, let's say at most t, if a particular battery is at most t, or let's say at most mid, if a particular battery is at most mid, then you can simply do the unsatisfied computers minus minus. You can do this. And otherwise, if it's not, then what can you do? You can add it to s. You can add it to s plus equal to battery, s plus equal to battery. And all you need to check is whatever the unsatisfied computers are there in this one, like some would be eliminated obviously during this if statement. The remaining unsatisfied computers, whatever are there, that whatever the time is required, what was it? It was s divided by mid, right? S divided by mid equal to, s divided by mid is greater than or equal to, s divided by mid is greater than or equal to t. Sorry, n. S divided by mid is greater than or equal to n. S divided by mid is the time you can run some k computers. If that particular k is greater than or equal to n, then obviously you can run n computers. So you can write it in a different way also. You can write it as written what was it? S greater than or equal to end n into mid, n into mid. You can write it as s greater than or equal to n into mid. All right, let's um, let's see if this works. Should we check it locally or should we directly submit it to LeetCode? Let's try running it in LeetCode itself. Okay, hopefully it should pass because everything seems right. It gave me a wrong answer. So let's analyze why did it give a wrong answer here. So we have start equal to 1, end equal to sum by n, while start is less than end, while start is less than end. Uh, if greedy check of batteries, greedy check is absolutely, it's perfect. Greedy check is absolutely perfect. And greedy check is absolutely perfect. Okay, wait, got it. It's not n, it's number of unsatisfied batteries. Sorry, unsatisfied computers. So let's replace this with unsatisfied computers. Now this should work. Still a wrong answer. Hmm. Let's add the equal to case. Maybe it would work. Yeah. So that's equal to was missing here. And it's passed. Alright guys, that's it for today. This was the LeetCode's problem of the day. Thank you everyone.